Hello everybody and welcome back. We're on the very last question here from the 2017 Euclid competition. We are on question number 10. Alright, what does question 10 have for us? Consider a set S that contains at least 4 elements, each of which is a positive integer, and no two of which are equal. We call S boring if it contains 4 distinct integers, a, b, c, d, so that a plus b is equal to c plus d. We call S exciting if it's not boring. Okay, so it's exciting if we can't find any 4 integers in the set so that a plus b equals c plus d. For example, 2, 4, 6, 8, 10 is boring since 4 plus 8 is the same as 2 plus 10. They're both 12. Okay. And 1, 5, 10, 25, 50 is exciting. Okay. I suppose if we listed out all 5 choose 4 sets of 4 integers, we wouldn't be able to add them all up. Okay, or we wouldn't be able to get 2 that add up to another 2. So I guess if we took all 5 choose 2, 10 pairs, and made their additions, we'd never get the same number. We'd get 10 different numbers. Alright, so this is actually quite typical of a question 10 on the Euclid, in that they just introduce a brand new concept to us. You know, sometimes it's a Jeffrey triangle. In this case, it's a boring and exciting sets. You know, there's lots of sort of things they do, but on question 10, I've noticed a lot. They tend to introduce a brand new thing, like an Anderson number. And they tell you its property, they give you its definition, and then for part A, they will often ask you to just, you know, ease yourself into the question, just, you know, is this set boring? Or give me the first Anderson number, you know, those sorts of things. And then B, and oftentimes there's a C, will add layers of complexity, and you'll realize, oh, these aren't just weird definitions, there's some hidden depth in there, there's calculations we have to make, but we also have to understand a lot of the theory of numbers. And that's what I would expect here. Now, what I want to get across to you is this. You can often do 10A with only a minimal understanding of high school math. Like, you can do it even if you know you're not going to get B or C, or even when you know you can't do 8 and 9. Okay, like 8 was a bunch of geometry. Maybe your brain just doesn't think that way. But you can often read a definition and do a very quick example of it. So I do encourage you guys to try 10A. And as I recall from marking this contest, a lot of I marked 8 to 10. I gave a lot more marks for 10A than I did for 8, because, you know, people can just jump in there and do 10A, even if you're the sort of person who at best is getting 10 out of 10 on 5 or 6. Okay? So let's take a look at 10A here. Find an exciting subset of 1, 2, 3, 4, 5, 6, 7, 8 that contains exactly 5 elements. Okay. Contains exactly 5 elements. So this will often serve as a nice little primer to understanding the concepts of exciting and boring. Sometimes, although they're getting better at this, sometimes if you read a later part, and this is especially true on things like the Hypatia, you can get a sense of how you were supposed to tackle this one. So what I mean by that is, you know, maybe we read C part here, and turns out, you know, all exciting sets must have this, like a multiple of 5 in them. So then going back to A, we realize, we must have a 5 in them. A 5 in this set. Anyway, find an exciting subset 1, 2, 3, 4, 5, 6, 7, 8. Well, I suppose we could just experiment a bit. I can't imagine it will be that hard, and so let's see what we can do here. So we got 1, 2, 3, 4, 5, 6, 7, 8. So our conditions only begin to fail when we have 4 or more numbers, and we're only being asked for a subset with 5. I think one thing we probably could do is sort of add up all these numbers and then make sure that we don't have any duplications, but there's going to be something like 28 pairs I'd have to add up. So I think I'm just going to start naively, and if I learn something, I learn something. But I think we'll start off with 1, 2, and 3. Okay. Now you can't have 4 because 1 plus 4 would be 2 plus 3. So 4 is out. But what else could we have? 5, 6, 7, 8. Well, could we have 5? I'm not saying 5 is the one we need, but could we have 5? Well, so that's akin to asking, is 1, 2, 3, 5 boring? If it's not, then it's still exciting. Well, if I were to choose an A, B, a C, and a D from this set, it would have to be 1, 2, 3, 4, 5. And in order for us to even try to get the same sum, you'd have to be adding the 2 biggest and the 2 smallest. Or sorry, the 2 middle ones. So 1 plus 5, 2 plus 3, no, that's not true. In fact, if I do any of these sums, we don't have a problem. Okay, so 1, 2, 3, 4, 5 works. I think 6, 7, and 8 would also work. Like 1, 2, 3, 6, 1, 2, 3, 7, 1, 2, 3, 8. So that doesn't mean I'm necessarily on the right track, but so 5's chosen. What else could I? Could I have 6 in here? Okay. Well, 2 and 5 is 7, and 1 and 6 is also 7. So 1 plus 6 would be 2 plus 5. Okay, so I can't have 6. And maybe I'll run out of 7 and 8, and then 5 isn't the one to go with. But because the set that we've got is so small, I think this is a viable strategy. Now, maybe there's nothing I can do, and it turns out 1, 2, and 3 shouldn't be allowed, and I'll have to try something else. I mean, there's lots of possibilities here, but I don't think it would be that hard, and we'll find out. But I mean, the numbers are small enough here that I think we can definitely tackle this one. Now, I don't want to have to keep sort of spying and saying, well, gee, 2 plus 5, oh yeah, that is the same as 1 plus 6. So I'm going to make a couple observations here. So one of my observations is this. If I have a set and this is exciting, then this set with a brand new one, let's call it X, is exciting if SA plus SB minus SC is not equal to X for all A, B, and C. Okay? This is sort of, I think this is a nice key observation, because if I have an exciting set, which I currently do, and I want to add to it, I just need to make sure that no matter what, because if I have this, if any A, B, and C satisfy this equation, then I'd be able to rearrange and say this, which would make it boring. Okay, but the left-hand side here is something that I can talk about without having to talk about, oh, am I going to put this X in? Am I going to put this X in? So if I go 1 plus 2, and in fact, actually, if X is bigger than all these S's, then in this equation I'll only have to consider SC being the smaller of the two, or a smaller of the three. So I don't need to do 1 plus 2 minus 5. But I do need to worry about 2 plus 3 minus 1, which is 4. And in fact, that's what shows you that 4 is the only one you can't add to 1, 2, and 3. But we could also do 2 plus 5 minus 1. And that shows you 6 is out. We could do 3 plus 5 minus 1. And that shows me 7 is out. And then we could do 3 plus 5 minus 2. And that would again tell me that 6 is out. And that's it. Those are the only equations we can make from here, with our smallest number being the ones that's subtracted. So 6 and 7 are not allowed, but 8 is. So 1, 2, 3, 5, 8 is exciting. If it weren't, I'd be able to take 8 and 3 of these other ones and add them up. So for example, if I'd had 1 plus 8 is equal to 2 plus 5. But that would have meant that 8 is 2 plus 5 minus 1. And that would have shown up on my list and told me I couldn't add 8. But it didn't. So I can add 8. So I don't know whether or not this star is just this star property here is going to help me with the whole problem, or whether or not it was just a nice quick way to work out 1, 2, 3, 4, 5, 8. Or sorry, 1, 2, 3, 5, 8. But if I had to explain what I was doing for A part, which, I mean, 10 says it's completely written, but you'll often find A is worth maybe 1 or 2 marks. There's not a whole lot of explanation you can give for it. But if I was going to give some explanation, I would say, this is my set. I start with 1, 2, 3. I show that, 4 can't be in it, so let's add 5. And then I show with this set, 4, show with 1, 2, 3, 5 that 4, 6, 7, and 6 can't be in, but that allows 8 to get in, so therefore it's exciting. Okay? So we might refer to this property again in a bit. But that finishes off A. 1, 2, 3, 5, 8 is exciting. Is it the only one? Probably not. And as I recall from marking, I think there's exactly one other one. And I think it was basically the same gaps, but in reverse order. So I think 8, 7, 6, then we skip over 1 to 4, and then the last one, 8. I think this is also exciting. But I'm going to try not to remember how we marked this, because I don't want it to affect me going through this. Okay, so that's A. And B. I'm going to read B and C together, because sometimes B can help you prove C and things like that, or C, knowing what C is can give you direction when you're looking at B. Prove that if S is an exciting set with more than 4 positive integers, because anything with 3, I guess, is technically exciting. Prove that if S is exciting, then S contains an integer greater than or equal to m squared minus m all over 4. Okay. And then C. Define rem AB to be the remainder when the positive integer A is divided by the positive integer B. For example, rem 10, 7 is 3, because when you divide 10 by 7, you get a remainder of 3. Rem 25 is 0, because 20 is divisible by 5. And rem 34 is 3. Alright, so they gave us plenty of examples, so we understand the remainder function. Let n be a positive integer with n greater than or equal to 10. Why 10? I mean, we went up to 8 here. 10 doesn't look like a number of this form. Anyway, so let n be a number greater than or equal to 10 for each positive integer k with k between 1 and n. Oh, geez. Define xk to be equal to 2n times the remainder when k squared is divided by n plus k. Determine with proof all positive integers n greater than or equal to 10 for which the set of all these xk's is exciting. Okay. So, just a quick comment about that. 10c is a mouthful. It really is. We got this brand new remainder function. Because it's talking about remainders, I'm initially thinking for C, and this is just what I'm talking about. I mean, I don't think B has anything to do with C. But I think with C, we're probably going to be doing a lot of modular arithmetic. And that's just arithmetic, but only with remainders divided by a certain number. I don't think B is going to be particularly helpful, because the form that they have in B, which is m squared minus m over 4, I mean, yes, it's got integers, but, it's got integers being squared, but that would only be able to show me that something isn't exciting if one of these if all of these x1, x2, x3 were less than n squared minus n over 4. And I don't think any of them will be, by the way, but that would only be able to show me that something isn't an exciting set. You see what I mean? B doesn't characterize exciting sets. It just it tells me, oh, if you've got an exciting set, you must have this. So if you don't have this, you must not have an exciting set. But C is asking to determine with proof when that set is exciting. So maybe B can do half of it, but again, I doubt it. But C is going to be a whole other ball game. And as I say, it's a mouthful. It looks scary, but if we choose to look at it in the right way, and I think modular arithmetic is going to do it, that remainder function gets less scary. These xk's, they're defined quite strictly, and I imagine there's a good reason for that. And something else that's catching my eye is the two n's there. But I'm gonna let C sort of stew in the back of my brain for a moment. Then let's move on to B. So prove that then S contains an integer greater than or equal to m squared minus m over 4. Okay, well, I'll tell you what this sort of looks like. This reminds me of triangular numbers. It really does. So you might be familiar with triangular numbers in that if I do something like 1 plus 2 plus 3 plus all the way up to n, that's the same as n times n plus 1 over 2, which is n squared plus n over 2. Now you'll say, oh, but root beer, we got a bit of a problem. 1, they have a 4 down here, and 2, they have a minus sign. That's true. But if I do 1 plus 2 plus 3 all the way up to plus n minus 1, suddenly that's n minus 1 times n over 2. And that gets me my n squared minus n over 2. And then you say, okay, yes, very, very good, fair enough, but what about that 2 down there? Well, I might be off in my connection. I really might be. But I think we'll have to... oh, by the way, it just occurred to me, if I wanted to set with m equal to 5, we'd do 5 squared minus 5 over 4, which is going to be 20 over 4, which is 5. So we'd need at least 5, 6, 7, or 8 included in our set in the last question. And actually, that doesn't help me. Never mind. I thought using B might have helped clarify A, but whatever. Okay. So this at least has me thinking, okay, well, what is this really doing here? We're adding up all these different numbers. Does this actually have a connection? And, maybe it doesn't. To be exciting, and this is, we should definitely be writing things up. So to be exciting, we must have no 4 elements or integers or whatever you want to say with A plus B equal to C plus D. And I mentioned this at the start when I was talking about, they give us an example here, 1, 5, 10, 25, 50. I said, okay, that's exciting. That means no matter what pair of numbers I get, their sum is unique amongst all other pairs. This is essentially what I was saying. There's going to be 10 pairs here. 5 choose 2. And actually, this guy right here is n choose 2. So that's the number of pairs for people who don't know choose notation. Number of pairs in a set of n elements. Okay. So, let's see if I can think through this. So, to be exciting, we must have no 4 elements that add up like this. So that tells me for any pair xy in my set, call it S, x plus y is unique. There are n choose 2, or sorry, no, m, because we're actually, they use m for the number of elements in S, don't they? There are m choose 2, which is m times m minus 1 all over 2. But where's the 4 going to come from? I mean, they have a 4 at the bottom. Where's that going to come from? I'm not entirely sure yet. But, we've got this connection. Let's write it out. Maybe we can get part marks even if we don't finish. There are m choose 2, which is this many, pairs of integers in S. If S is exciting, then we get this many sums x plus y, and each is unique. Right? Because if there were a pair u v that also had the same sum, then I'd have u plus v is equal to x plus y. Okay. So now where am I going to get this over 4? Because I definitely think I have the right connection. M squared minus m over 2 is how many of those sums we get, but how do we get greater than or equal to this? So it's like they halved it again. They divided it in 2. So now I have m squared minus m over 2 different sums. And doesn't seem, by the way, my initial comment about triangular numbers, that connection sort of didn't work out, but my very first comment about the number of pairs having to each have their sum being unique does seem to have made sense. Sometimes there are similar expressions for the same thing, and that's sort of what happened here. So this has nothing to do, at least it doesn't look like it, with triangular numbers. Okay, so this part of the observation not helpful. Okay, so I know those sums have to be unique. There's m squared minus m over 2 of them. And for some reason, we're talking about m squared minus m over 4, which is 1/2 of m squared minus m over 2. So where would the half come in? So there needs to be an x that's greater than this. So, okay. I think. So they told us, they did tell us this, right? That each thing has to be positive integers, no two of which are equal. Okay. Each x plus y is positive So, since there are m squared minus m over 2 positive and unique sums, then at least one of them is as big or bigger than m squared minus m over 2. Right? I can't guarantee that this number is one of the sums, even though it is always an integer. But, I mean, at bare minimum, one of the sums is 1, one of the sums is 2, one of the sums is 3, and so on. Since they all have to be unique, there's got to be at least m squared minus m over 2, or there have to be exactly m squared minus m over 2 different sums, and this is the smallest list of positive integers of m squared minus m over 2 positive integers, and even this has something that is as big or bigger than m squared minus m over 2. So I'm going to call this sum z. Then there is an x and a y in S. So x plus y is equal to z, which is greater than or equal to m squared minus m over 2. But then one of x and y, I mean, let's not phrase it that way. Let's say one of x and y is bigger. So suppose x is greater than or equal to y. If not, then just rename them. So x is greater than or equal to y. So x plus, so 2x is x plus x, which is greater than or equal to x plus y, which equals z, which is greater than or equal to m squared minus m over 2, and that tells me x is greater than or equal to m squared minus m over 4. Just divide both ends of this inequality by 2, and that's why it's over 4, because it really is a half of that thing. And that's exactly what we wanted to show. We wanted to show there is an element in S that is greater than or equal to m squared minus m over 4. Okay. It took a little while to get there, and I mean, it's sort of a red herring there in that you might initially say, oh, that m squared minus m over 4 sort of looks like the sum of a certain number of natural numbers. That really didn't factor into it, now did it? No, and triangular numbers didn't help us out there. It was understanding choose notation. You know, when I say I've got 6 elements in my set, you can say, okay, you've got 6 times 5 over 2, 15 pairs that you can pick. And if you didn't know that, you would have been at a little bit of a loss and probably, I think, chasing triangular numbers or something like that. Okay. So that's B. That's fine. Let's take a look now at C. So C had these xk's, which was 2n. I said I was going to talk about this 2n. And the remainder of k squared, I think it was n here, plus k. That's the formula, right? 2n times the remainder of k squared, n plus k. Okay. So a couple things to note, or a couple of things that immediately catch my eye. One, we're talking about k squared, remainders of k squared modulo a particular n. This is actually something that's studied in math a fair bit. I think Legendre symbols might be something that might interest you if you want to look up more of this stuff. I don't quite remember exactly what those are, but I think it's the number of, it's for primes, but it's the number of numbers in this range so that a squared is congruent to 1 mod p. I think it's something like that. I think that's something like that. I'm not entirely sure. But I know this is something that's studied, so this is a nice mathematical concept. And the other thing that makes me interested is, okay, this remainder here, he's going to be between 0 and n minus 1. And so this 2n here, it's sort of like units digits, tens digits, and things like that. This 2n times this is sort of like this digit over here, and these k's are sort of like our if we think base n, these k's will only ever appear here, and this remainder stuff will only ever appear here because it's n times something. I'm sure we can make that more exact if we need it, but that's the thought. And that's why I think this looks more complicated than it is, but I think the remainders are only ever going to play with themselves, and the k's are only ever going to play with themselves. And I'll show you what I mean by that. To be exciting means that our set here is not boring. That's literally the definition they gave us, but we'll restate it for a moment. So, since they want us to figure out exactly which n give us exciting, it might be easier for us to instead figure out which n make that set boring. Okay? If it turns out that squares always make that set boring, then anything that's not a square must make it exciting if we can get an exact characterization. So, although they're asking us about exciting, maybe we should look at boring, because boring is the one that's sort of a positive property. I mean, if you're boring, then you do have a plus b equals c plus d. If you're exciting, it just sort of shuts down the arguments, what I would refer to as a negative property. It's just not boring. These a, b, c, d's don't exist. No, they don't exist. So I think we'll focus on the boring. We'll show which n give us boring first. Okay, so the set is boring if we can find, well, I'm not going to call this a1, or sorry, this x1a. I'm just going to refer to its little letters. So if we, the subscript, if we can find a, b, c, and d, and it's between 1 and n, so that xa plus xb is equal to xc plus xd. Now, I could rearrange this and make like I did in A part, but I don't think that's going to be particularly helpful, because in A part, this sort of rearrangement helped us add elements to the set. We're not adding new elements. And by the way, if we then talk about the set with xn plus 1, completely different numbers here. Completely different numbers we're going to get here, because it's all based on this remainder here. So it's not, oh, can we add xn plus 1 into this set? No, it's when you change your n, you change all the elements here. So we're not adding anything. So that's not particularly helpful, although I suppose we could go all the way and get an equals 0. Also thinking we could probably give better names. Well, no. I was going to say we can order them, but I don't think A and B are the smaller ones. I don't think A and B being the two smallest is going to help us. But let's look at this expression here. So that tells me 2n remainder of a squared n plus a plus 2n remainder of b squared n plus b minus 2n remainder of c squared plus c oh, I guess it would be minus c. Got to be careful about those brackets. Minus 2n remainder of d squared n minus d has got to be equal to 0. Now, I'm gonna work mod n. Now, each of these things with the remainder has a factor of n, so it's not going to matter. So modulo n, we see a plus b minus c minus d is congruent to 0, because it's actually equal to 0. But that doesn't mean that it actually is equal to 0. It just means that it gives a remainder of 0 when we divide it by n. Right? Because the whole expression is equal to 0, and then when we ignore everything that already is 0, gives us a remainder of 0 when we divide by n, what's left is a plus b minus c minus d. So this expression is true, although maybe a plus b minus c minus d is actually equal to n, or is equal to negative n, or is equal to 2n. But the point is it gives a remainder of 0. But these a plus b plus c plus d's are less than or equal to n. So a and b are definitely less than or equal to n. C and d are at least 1. So a plus b minus c minus d is less than or equal to 2n minus 2. And c and d are less than or equal to n, and a and b are at least 1. So a plus b minus c minus d is at most, is at least 2 minus 2n. Okay. So that sort of limits us a bit. We can only have, so if a plus b minus c minus d, because it's congruent to 0 mod n, we'll either have a plus b minus c minus d is equal to negative n, 0, or just n itself. Okay. But see, I was really hoping when we did this that analysis that maybe it would just pop out to be 0, but it's not. But what I can definitely say for certain is that it's not congruent to 2n. It will never be negative 2n, it'll never be 2n, it'll never be a multiple of that. And I think that is why they do 2n times the remainder instead of n times the remainder. Okay, so I'll show you how this plays out, and I'm actually getting kind of excited now. Okay, so now, and maybe I could have just done this from the start, modulo 2n, we see, actually, we don't even need modulo 2n. I think I'm going to let r be the remainders. I think this will just save me a lot of writing in time. Subtract that. And then I don't know. We'll say L for the leftovers. Okay. So we know that 2n times r plus L is equal to 0. Therefore, L is equal to 2 minus 2nr, but r is an integer. So what does that tell us? That tells us 2n divides L, but 2n doesn't divide n or negative n, so therefore L has to be equal to 0. Has to be. So if that's the case, then 2n times r plus L is equal to 0. Well, that just tells me 2n times r is equal to 0. And the only way that's going to happen is if r is equal to 0. So now I've got, this sort of is what I was talking about. The remainders are not doing anything to these a plus b minus c minus d's. They're sort of playing on their own. We can keep them as r. We can keep the regular numbers as L, the leftovers. And they're not really interacting. Whatever the remainder of c squared when we divide by n is, it doesn't really have any impact on a or b. Okay, so L is equal to 0, R is equal to 0. I would say that's probably a key fact to note, and in the proof is probably worth at least 1, is arguing down to this. Okay, what else can we do? So we know a plus b minus c minus d. So a, b, c, and d are a boring pair in 1, 2, 3, 4, 5, 6, 7, 8, all the way up to n. But what can we say about r? R is all those remainders. Well, I don't like those remainders, and maybe I can play with them mod 0. So r is really just a squared plus b squared minus c squared minus d squared when we divide by n, mod n. Is there anything we can do with that? I know it's got to be equal to 0. And I guess, so, because it's got to be equivalent to 0 mod n, because r is in fact equal to 0. And if we work with these ones here, they're also congruent mod n. What can we do? What can we do? Is there some way to factor this? I'm not seeing anything to factor right away. That doesn't mean there isn't anything. Well, alright, maybe that's the wrong step. But a plus b minus c minus d is equal to 0. Maybe modding and ending it isn't going to help me. Well, I could say a plus b is equal to c plus d. I already said that this is boring. Could I reduce the variable count in some way? I mean, I have this relationship. It's pretty strong. So I might we already used x, and let m be what we need to add a2 to get c. So let m be c minus a. Then we get a plus b is a plus m plus d. And that tells me that B minus D is equal to M. Okay, but we have this equation here. A squared, we'll do minus C squared, and then B squared minus D squared, mod N. And that's going to, I can take out, all right, I'm going to rearrange this because I'll do A minus C here. And then that would rearrange to give me so this would become negative M, so we'd bring it over to the other side, so M would be equal to D minus B. Alright, so I'm going to say this is A minus C, A plus C. Hey, oh no, that's A minus C is there. I was hoping that'd be helpful. And then I'm going to change this to minus D squared minus B squared mod N. But now I can say, that's A minus C, A plus C minus D minus B, D plus B. And that's, we take out, both of these are M. So A plus C minus D minus B, which is remarkably similar to this equation, but it's not that equation. Now, I do this at the cost of working mod N, which might not be the best thing, but then again, we were working mod N a little while ago, and we still managed to show both R and L are equal to 0. Okay. Now, what can we do? Can M be equal to N? No, it can't be, but I can't exactly get rid of M either. If N were a prime, I could, but it might be that, so for example, I could have something like, and I know they said N has to be greater than or equal to 10, just bear with me for a moment. If N is 6 and M is 2, well, suddenly I've got a 2 here. I can't say that this thing is congruent to 0 like I normally could. I can't divide both sides of this equation by M. But I can definitely say then that this is a multiple of 3. So, I don't know, maybe looking at this with composite numbers might help. Okay. So, I'll say something like, suppose N is equal to, I don't know, U times V. Actually, no, hold on. A is at most N, C is at least 1, and A is at least 1, C is at most N. These two facts combine to tell me that negative 1 plus N is less than or equal to M, is less than or equal to N minus 1. Therefore, N doesn't divide M, and I think that's important to note. So let U be the greatest common divisor of N and M, and V is just going to be N over U. So what this statement here tells me is A plus C minus B minus D mod N tells me that since U divides M, therefore V must divide A plus C minus B minus D. And if we wanted to, we could say, well, I mean, if you thought that's a bit of a leap, which I don't think it is, but if you thought it was a leap, this equation really means there exists a K so that NK is equal to M, A plus C minus B minus D. So NK minus M A plus C minus B minus D. So U divides this whole side. Wait, what? U divides this side. So U has to divide this, but then doesn't V have to divide? V has to divide something. Oh, right, I subtracted. Doy. Divided by M. So then this is going to be V times something times K, A plus C minus B minus D. So V divides A plus C minus B minus D. So now I think we have to work mod this V here. And depending on what U and V can be, that might affect our ends. But now let's working modulo V. Okay, so A plus B minus C minus D is equal to 0, so therefore it's congruent to 0, mod V. But I've also got A plus C minus B minus D is congruent to 0, mod V. And I can add these two equations up. The C's are going to cancel, the B's are going to cancel. I'm going to be left with 2A minus D is congruent to 0, mod V. Alrighty. So what does that tell me? Well, unless V is even, we'd need A minus B to definitely be divisible by V, but maybe A minus D is divisible by V over 2. Same sort of argument from before. Is there anything else we can do here? I also know U divides M, which is A minus C. So now I have a relationship with A minus C and an A minus D. And this is also, what is it? D minus B. So what can we do from here? And do I have to do a separate case when V is even? I'm not sure. Alright. So unfortunately I can't really add these equations together either and do anything with it. But I know that V is not 1. Right, so V actually means something. Because N doesn't divide M, which I didn't write properly before. Okay. By the way, all of this is coming together to make me able to say, okay, if you let A be this and D be this, and it satisfies this condition, and you let A be this and C be this, and it satisfies this condition, then you have a boring set. Okay, just remembering to keep our eye on the prize. Why are we doing all this modular arithmetic stuff? I'm trying to better understand, if I had a boring set, I'd get an A, B, C, and D that do this. What do those A, B, C, and D look like? Because what I want to be able to do is come back at you and say, okay, you think 14 is gives a boring set. Well, let me tell you, if you take x2 and x5 and x7 and x9, then this all works out, and it is in fact boring, that sort of thing. That's what we're trying to do here, and I don't think I've made that entirely clear. Okay, so we need this U and this V here. What can we do now? So I want to be able to, if it's going to be exciting, then I would need to be able to conclude that A and D are actually equal to 0, something like that. So what do we got? We've got n is equal to u times v. Now, I know v isn't equal to 1, but maybe u is. What if n is prime, then since m can't be equal to p, and u is the greatest common divisor, u's got to be equal to 1. So v is equal to n, which is prime. Therefore, 2a minus d congruent to 0 mod n, but n is greater than or equal to 10. Therefore, n is odd. And that tells me a minus d is congruent to 0 mod n. But then by the same reasoning we've been doing a whole lot today, a minus d has got to be in this particular range, but a minus d is divisible by n. Therefore, a minus d is equal to 0, and that tells me a is equal to d. But but to be boring, we must have a not equal to d. But this is a direct consequence. If n is a prime, you can't be boring because all our conclusions tell us that a is equal to d. So, for example, there, not p, n prime is exciting. Now, are these the only ones that work this way? I don't know, but I have at least shown something. And that's, so when we were prime, that sort of restricted our u times our v, what we could have. So what else can we do? Well, so that's a nice conclusion there. Now let's stare at this again. N equals u times v. I know v isn't equal to 1. And I'll assume that u is not equal to 1 as well. So now we're looking at composite n's. And maybe we'll have to break this down into other cases, I don't know. But we can certainly look at these guys being composite. What do we need to have happen? We need we need u to divide a minus c, and I'd like v to divide a minus d, although, maybe there's some oddness or evenness there that we'd be unhappy with. And this is also d minus b. Okay. Well, what can we do? If I let c be 0, I could let a be u, but c can't be 0, so I don't know. I'm just trying to satisfy these conditions in a really silly and obvious way. Let's let a minus c actually be equal to u. So let's let m be u, and a minus d be v. Because that would definitely work, wouldn't it? It would satisfy all our conditions. Now I can't let c and d be 0 to make a both u and v, but I could make a n. Or should I still be trying to show something like a minus d is equal to 0? So I need to satisfy these conditions. I don't know enough about u and v, but I know if I had a u and a v, I could do something like this. Let a be n and let c be, what would we need? N minus u. D would be n minus v. And what would b be? B would be n minus v minus u again. I'll write it this way. So, does that work? Well, c and v are both greater than 1, so A is definitely not equal to B, C is not equal to B, A is not equal to C, A is not equal to D, but if U equals V, then I guess C would be equal to D. So that's, I don't know, that's a bit of a problem. So maybe we have an extra case where U and V are equal to each other. And that probably only happens for a certain number of numbers. When does that happen? So no matter how I write n, as long as its two factors aren't 1, they would have to be the same factor. Prime squares? Yeah, prime squares. So I think we'll have a separate case where n is prime squares. So maybe the answer is it's exciting if n is prime, or if it's the square of a prime, and then if it's any other type of composite number, it turns out to be boring. Now, I haven't finished this off, but these are the thoughts going through my head. Okay? And so it's important to be able to jump to a conclusion like that, so that if time gets called and you're in the middle of something, you say, you know, I think it's n is prime squared, and so forth, and you can maybe put a sentence there explaining, even if you don't have all the calculations done. Now let's just double check. So if we can write n is u times v, with u and v both greater than 1, and u not equal to v, x of n plus, well, really, what do I need to have happen? I need r to be congruent to 0 mod n, and I know I need L to be equal to, well, L is just A plus B plus C plus D, or A plus B minus C minus D, and we need L to be equal to 0. These are the two things we need to have happen. Let's show that they happen with A being n, what did I say, B is n minus U minus V, and C is n minus U, and D is n minus V. And B does exist. B is not negative, right? So if this were less than 0, then n would be less than u plus v. But that doesn't happen unless... That only happens if one of these is n and the other one's 1, and that can't happen. Okay. I'm a little more convinced that these are distinct, but maybe we need an argument that, you know, to show b is greater than 0. Maybe we need something like that. I don't know. These are all distinct, and a plus b minus c minus d is n plus n minus u minus v minus n minus u minus n minus v. The n's all cancel. Negative v and negative v cancels, and negative u and negative u cancel. So yes, L is 0. And now let's talk about those squares. So r is congruent to n squared plus n minus u minus v squared minus n minus u squared minus n minus v squared. And I want to show that this is congruent to 0 mod n. That's what we needed to show. Okay, because, yeah. Right? Or did I need to show that this is actually equal? No, because when I do the remainder, that's what n is. Well, hold on. Let's just work out all these remainders. Remainder of n squared, n, that's going to be 0. No worries about that. Remainder of n minus u minus v squared n is going to be the remainder of n squared minus 2nu minus 2nv plus u squared minus 2uv, plus 2uv minus plus v squared mod n. But that doesn't contribute anything. No, no. And u times v is equal to n, so that's also a no. So this is the remainder of u squared plus v squared mod n. Remainder of n minus u squared is the remainder of n squared minus 2nu plus u squared. And so those guys don't contribute anything. So it's the remainder of u squared n, and n minus v squared is going to have a similar remainder. It's going to be v squared. So this is u, this is v squared n. So yes, r is just this plus this minus this minus this, but that's going to be u squared plus v squared minus u squared minus v squared. So r is indeed going to be equal to 0. Therefore, n being, if I can write n like this, and u not equal to v, n gives a boring set. Okay. And now there's the other case. If we can't write n is uv and with uv not equal to 1 and u not equal to v, then we've got to have n is a prime squared. Right? Because suppose not. So suppose I have a factor of n. Actually, suppose I have a prime factor of n. Suppose p divides n. I'll show that n has to be p squared. Right? N can't be 1, because n's got to be greater than 10. So suppose that p divides n. Then either n over p is equal to 1, which I'm not dealing with. We've already talked about n being prime. Or n can be written as p times... Well, sorry, my point is... So some p has to divide n. Then I can write n is p times n over p. Now, if it fails this condition, either n over p is equal to 1, and n is prime, or n over p is equal to our other factor p, therefore n is p squared. So now we're going to consider n is equal to a prime squared. So what equation did we have before? We had 2 times a minus d is congruent to 0 mod v, but in that case we'll choose p here. And we had a minus c is congruent to 0 mod p as well. We had d minus b is congruent to 0 mod p. But we have all of these. Now, n is greater than or equal to 10. So n is not equal to 4, which is 2 squared. Therefore, p is odd. And that tells me I can divide by 2 here without changing the 0. So a minus d is congruent to 0 mod p. Now, what could we have? So either we can rearrange these equations and show that, for example, a equals d again, in which case then our set is exciting, or I can come up with sort of that n. So the problem is I couldn't do n minus, a being n, b being n minus p, and c being n minus p, because d would also be n minus p. That's why the u and v stuff that we did before, we needed u not to be equal to v. And that's why that didn't work. So maybe there's another way I can work this out. Maybe there's another thing I can come up with. that you know, A is this, B is this, C is this, D is this, and so the prime squared case is still boring. But maybe I can work out these equations and show that, you know, if you have xa plus xb equal to xc plus xd, the a and the d have to be equal to 0, which is what I showed for the prime case. So I'm not entirely sure where this one's going, but we're going to explore a bit. Now, I can't really add any of these equations together. I mean, I certainly can, but I'd be trading. I could add, you know, a minus d to the b to the d minus b and talk about a minus b is congruent to 0. So at the end of the day, I think I'm just looking for all my a, b's, and c's and d's to differ by a prime p. And I think that's possible, so now I'm thinking the prime squared case is going to be boring. Let's see what we can do. We need them to differ by primes, so let A be p squared, and then c can be whatever the heck we want, as long as it's also a multiple of a prime. So, actually, I'm going to let A be P, B be, no, because I need, A and B are on the same side of the equation, so I need, I'm going to let C be 2P, I'm going to let D be 3P, and I'm going to let B be 4P, and P is at least 5, right? Actually, maybe that's why they chose n having to be greater than 10, because that avoids the n is equal to 9, in which case p is equal to 3, in which case this b is beyond our range. So, actually that shows quality planning, and that explains where the 10 comes from. So, these should satisfy all the equations. Now, I notice a plus b minus c minus d is equal to 0. 5p minus 5p is equal to 0. And the remainders here, oh, now the remainders might be tricky. Remainder of a squared p squared, that's going to be the remainder of p squared, well, that's going to be 0. And then we're going to do 2p squared, p squared, well, that's just going to be 4p squared, p squared, and that's also going to be 0. Oh, this is working out quite nicely. 9p squared, p squared, that gives us a remainder of 0 because it divides evenly. And then the last one, 16p squared, p squared is equal to 0. And so that would tell me r is equal to 0, and my equation is satisfied, and all of these are unique, so it's boring. So as long as I take out the filler calculations, I can sort of sum up. X1 up to xn is exciting for n greater than or equal to 10 exactly when n is equal to a prime. And it is boring otherwise. I was really hoping that it would be prime and prime squared, because so many times you work modular arithmetic with modular arithmetic, and the primes are just the interesting, the exciting case. And so I was really hoping prime squareds would have a chance to shine, but no, we've and there's probably other ones you can do, but P, 2P, 3P, 4P, that worked out brilliantly. All right, so that wraps up question number 10. Comments on it, kind of each part had nothing to do with the other parts. One thing I didn't make a comment on, in A, our answer was 1, 2, 3, 5, 8. And I thought it at the time, but I wasn't going to mention it until we needed it in B, which we never did. That's Fibonacci. And we didn't need a Fibonacci argument. I think you could probably play around with it. I think, for example, the smallest set of m integers that is exciting would be the first m Fibonacci numbers. I think that's probably true. How to show that, not entirely sure, but I think that's true. Didn't use that fact. And in B, we showed that there has to be an element that's greater than something, but didn't use that at all in C either, because in C we were handed a set, we weren't creating sets, so it didn't help us do anything with it. And yeah, I mean, it's a good concept, but I prefer a little more connectivity in my questions when they introduce a brand new concept. But overall, it wasn't a terribly bad question. I would say C part, it was quite obvious we needed to go modular arithmetic. And then it's a question of, can we work through all these little cases of, can U be 1? Can V be 1? What if U and V aren't equal? That sort of stuff. And that was a bit of a slog, I'm not going to lie. But it all worked out. We had 3 cases we had to work out. Primes, prime squareds, and everything else. It's not so bad. Yeah, and that wraps up the 2017 paper quite nicely. We're all done. It's been a good paper overall. I don't think it's that bad. I was in the marking room for some of these, and some of the questions done well, some of the questions not so done well. I think I saw maybe one person solve C, and I remember I was talking with the remarkers. I think there was one person that so I was talking to one of the remarkers, Robert, and at lunch on the last day of marking, he said he did manage to see someone who got full marks on 10. So such people do exist, but I think 10 was not one of the better done ones, which it shouldn't be. It's supposed to be the hardest question on there. But yeah. Anyways, 2017 all done. Stay tuned for more math contests, and in the meantime, have yourselves a wonderful day. I'll see you guys later.